Afternoon to all. Now we will continue with another topic on the advanced process control techniques. Now moving into the other types of methods, basically the modern advanced process control techniques, and which we have seen before, basically model-based control techniques. And the next one that we're going to talk about in this talk is about the generic model control technique, which is also GMC, sometimes called GMC. It's a model-based technique. It depends a lot on the model, and it is basically totally different from the conventional PID method. So it's an advanced control method, and also not a classical method because it's not no updatation of reference to the conventional method, as we've seen before. For the cascade ratio feedforward, which have some relationship or some connection with the conventional PID controller or scheme itself. But it's in general, model control technique is totally dependent on the model itself. It does not have any relationship with the conventional controllers, nor is the scheme got any connection with the normal classical model, process control techniques that we have seen before in the conventional process control class. So this is the topic on GMC that we're going to talk about. A little bit basic idea of what GMC is about, and I was showing some application of GMC. Okay. Basically, GMC is a model-based control strategy, as I mentioned just now, and it is a system that uses linear and non-linear models for system to compute the control action. So it can be used for linear. It can also be used on non-linear models, as long as we have a model, basic required good model, then it can be used for any one of them. And inside the computation or inside the formulation of this GMC, we have the also the tuning parameters, which are called K1 and K2, that we also have to need to tune it to get the right tuning or to get the right response that we want using the GMC method. GMC method basically developed by professors in Australia quite some time ago in the 70s, and it's been used extensively in some application, non-linear application. Even there are some online application, a few online application, but of course a lot of work on simulation on a theoretical basis and so on. And it's a practical method. The only issue we'll talk later about the disadvantage we'll talk about later of the need to have a model and a few other things. And the biggest advantage basically is that the GMC can directly use non-linear models of a process to determine the control action. And these non-linear models do not need to be linearized. That's the most important thing. You just use the model as it is to formulate the control action using this GMC method. Whereas, as we've seen before, for conventional methods, if you have a nonlinear system, you need to linearize it, because the basic of PID is mainly for linear systems. The Laplace transformation methodology in the block diagram mainly for linear systems. If non-linear, they have to be linearized, and with that, there's a lot of disadvantage. Not being not linearized, so the accuracy will be lost, and linearized is only on certain basic regions of the point of linearization. It works in that point, doesn't work in other points, and again, linearization may not be so simple for a complex system, may be very difficult to achieve, may be very difficult to get accurate parameters, may be very difficult to get it to work on a bigger range of control action, bigger range of operating regions, and linearization. As we said before, the accuracy will be lost definitely because linearized system will work for some region, for some system, but for some other system may not be that good and not be generally used. And stability, maybe also face stability problems in very non-linear systems, non-linear regions, and so on. So that's a disadvantage of using the conventional control for non-linear system. But for this one, we are using the system itself, the model as it is, without linearize. So we expect the accuracy to be much better when using this method, the generic model control strategy. And whatever it is, the limitation, of course, other being the model, but even if we have the model, limitation is that the application of the GMC is limited to systems which are linear in control or relative degree 1 system. We'll see that later, which means that basically when we use the model, we should be able to get the U implicitly with respect to the other parameters. We should not get the U in a non-linear form and things like that. We should lose the advantage of using this method. We should get the U immediately being linear in control, that we can formulate it just as it is. We may have non-linear terms, but at least the U itself does not need to be square root or the cube root or whatever that loses its direct formulation for the U. So there's got that limitation. Not everything can be done, which is why it's relative degree 1 when you talk about nonlinear differentiation. When we differentiate it on the first order, then the U should come out visually, that we can straightforward, that we can use it immediately. If it cannot, then it's not the relative degree 1. We may have to differentiate again as relative degree 2 and so on, which no more applies for the GMC method and so on. So this is a limitation, which means that it can be useful. It's a good method, a very nice method, a useful method as long as there's a model and it can be linear in control. Let's say. Other than that, we are not able to use it, and so that's why some limitations in using GMC for all systems, which is not possible because of this requirement or limitation, would say. And also the requirement, okay, or also can be said part of limitation. We need to have the reasonable process model and parameter. A good one, of course, or not a reasonable one, not totally out and not totally inaccurate, not totally unusable. So it has to be somehow reasonable process model and parameters that we should be able to use. And of course, we need to measure the control variable. That's almost control system we need to measure. And that's a requirement for this one. The measurement of the control variable is needed for us to be able to implement the GMC method for chemical process systems. Okay, next. We look at it. The system, ODE system, whether it be linear or non-linear, can be expressed in its form. X dot mean the differential of x, the state variable, which equals a function of the state variable, the control variable, and time. Okay, it's a dynamic system. We talk about dynamic system, of course, because we're dealing with control of the real world, which is dynamic, not steady state. Steady state is a specific condition, but on the whole, it's a dynamic system. So this is the general equation, and the y output is a function of the state variable. Okay, this is a general formulation for mathematical systems, in terms of the ODE and the output of the system. So what is happening is that in the GMC algorithm, the control U is chosen such that we follow this formulation. This is the main formulation of the GMC. Y dot is equals to K1 epsilon, which is the error, plus integrate K2 epsilon and dt. Okay, so this is the formulation that has been the we can say novelty contribution of GMC is coming up with this method. It looks close to the PI. It's not a PI, but some maybe ideas from the PI itself. The tuning has got no relationship to the PI controller, but formulation slightly close to it, but it's not exactly. But whatever it is, this is the formulation, the most important formulation we need to come up with for the GMC. It has to follow this, and the epsilon is just the y set minus the y. Y depends the required value, set point, or whatever it is. So this is the error that has to be taken care on the right side. And this on the left side is the differential of the output. Okay, so this is where we mentioned just now, and when we need the first order relative first order system, then when we differentiate, we should come up with the u on this side. Okay, to be able to apply this method. Okay, so we see just now we get y naught, and we formulate the two equations. We'll get dx over dx times dx over t partial fraction because it's a function of x and t. Okay, and multiple, and if we further simplify it, it's partial hx over dx times dx over dt, which is the formulation just now, is the function of x, u, and t. So whatever it is, the formulation of the GMC is equals to dHx over dx, okay, times the function x, u, and t, the function of the model system that we've seen in the first one, ODE. And if we go a bit and simplify it slightly for any non-linear system which is linear in control, okay, now we say linear control, the u can be formulated in terms of the fx and gx in this form. So this is where we talk about linear in control. We can formulate u in terms of the other variables or the functions of other variables. Therefore, we can obtain just now, we've seen the formulation of GMC, K1 epsilon plus integrate K2 epsilon t from 0 to tf, whatever time frame that we are integrating it to. And this is equal to dHx over x times fx plus gxu. Okay, so we saw dHx over dx times fx ut, which is given in this form. So you times by fx plus gxu from the previous slide. As I said, I can't go back to the previous slide because it will lose the recording. So you can remember the previous slide or look back for yourself. You can see what I mean. And in many cases, the dHx over dx equals to 1. Okay, that's y equals to x, not function of x, but x. So many cases this is so. So basically this becomes 1. And if we get into the GMC formulation, okay, so we can see that this part K1 epsilon t plus integrate K2 epsilon is equals to fx dx. Since this is 1, so just left with fx plus gxu. This is linear in control, and we will get u equals to, just formulate it in from here, is K1 epsilon plus integrate K2 epsilon minus fx, the function fx, over gx, another function of x. Okay, this gx is associated with the u, fx is the one not associated with the u. U is the manipulated variable, the one that we're going to manipulate to be able to get the system under control, or to follow the set point, or to reject disturbances, as we've seen before in the other control system where the u is the manipulated variable. So this is the formulation, GMC formulation for this sort of equations. The direct one. This is general. Fx can be anything, gx can be anything, as long as the u is linear in control. This formulation is acceptable and achieve the requirement for using GMC. Otherwise, we are not able to use the GMC if the u is not linear in control. We cannot formulate u in this form. We are not able to get the GMC method. Okay, and if you're not linear, non-linear, then we can't formulate in this form. It will be difficult to formulate, be inaccurate, and so on. But this linear control, directly we can formulate u in this form. Okay, just knowing what we need to know. we know the error, the set point minus the actual measurement. We need to measure the control variable. We need the tuning parameters. We'll see how we'll do it later. And we need to have the function fx, which is given from the equation, and the function gx should be given by the model. As I said, we have a good model, we have a good fx and gx. We can be used directly into this GMC formulation without any problems. So dependent a lot on the accuracy and the accurateness of the model and the parameters inside it. Okay, for the tuning, we want tuning the one if we want to control an output 36 point by 20 minutes and choose okay zeta extend and t over tau equals 0.25. So it's given that k1 is in this form, 2 zeta over tau, k2 in this one. This is the formulation of part of GMC that we use to help us get the tuning parameters. So if we have 20 over tau equals to 0.25, 20 times 20 minutes over tau to 0.25, so we get the tau should be 80 minutes. If the tau is 80 and we choose zeta 10 and 2 zeta over tau is 1 quarter, and k2 is 1 over t squared is 1 over 80 squared. So this is how you get the formula. This is taken from the graph. The graph we say the set point we want it within 20 minutes, and then we choose the zeta part, then from there we choose what should the t over tau be. Okay, from this graph. This is a common graph. Normally this is a graph that is being used for GMC, which is more or less accurate enough in most cases. So you can see here different zetas, different performance in general performance for most systems. So if you choose just now zeta equals to 10, okay, fast damping, and then so when we want to get the set point, then it should be t over tau equals to 0.25 here, okay, to reach the set point, right? So from there, and we said that the time that we want is 20 minutes, so we equate that 20 minutes, and so we get out that k1 and k2 as I've shown you previously. From there we basically get these tuning parameters that is being used for the GMC method. Okay, as I said before, it's nothing to do with the tuning that you normally use for P, PI, PID, but it's related to that formulation that we use K1 and K2 formulation for the GMC method. And this is graph, normal typical graph that we use to get roughly the K1, K2. This is again just like we do for tuning using Nichols and so on. This is roughly an initial estimate for the tuning. After that, we may need to fine-tune it a bit more to get better result, to get more the profile that you want, to get more the sort of overshoot or time of response that we want. We may have to a little bit fine, just like Nichols and other methods. These are initial estimates, not the perfect estimate, of course, because there's a lot of inaccuracy in this. It's an empirical method. But having those initial estimate, and then we can be able to slowly fine-tune from there, and not from anywhere, not from just blind estimation, but with this some sort of required estimation, we can get initial tuning, and from there we can fine-tune a bit. Of course, again, depend on the zeta. We want a quick damp or a slow damping or oscillatory response. Up to us, we decide what sort of response. So if we use 10, we are asking for a more vigorous damping of the system, okay, a very strong damping. So we should expect to get that damping for our system as well. So this choice will we decide what sort of response we want, and from that we decide how to tune the K1 and K2, what the values. From that we should be coming up with the response that we are looking for, because it depends also a lot on the model, and also depends on the K1 and K2 that you have chosen in your method, the GMC method that you've chosen. So if we are going to take an example, non-linear system, of course, that's the best example. Again, this can be used for linear system as well, But if we take a non-linear system as an example, and CSTR has a normally good CSTR system, so we get this equation for mass and for energy balance. Okay, so these are the dimensionless constants of the system. Okay, and basically this would be the this energy balance, and this would be the mass balance. Okay, these are form already dimensionless constant, but you can go back and put it down into the normal ODE or mass balance. So it doesn't have to be dimensionless. This is a typical dimensionless just to make it easier. It doesn't have to be, it can be any ODE system, and these two variables x1, x2, as I said, this represents temperature, this represents the concentration, x1 and x2, and this is the ODE. If we do mass balance of the CSTR, this is what we're going to get in the dimensionless form, and this is what we're going to get for concentration in dimensionless form. So we have two options now. First option, we would like to control the x1, which is the temperature in this case. Okay, so that's mean we want to control x1. That means our y is equals to x1. This is control, and this is the one that we are interested in to achieve the set point and so on. Okay, so if we follow through, we would like to implement the GMC method for this sort of system. Okay, what we do, we'll have to get the y dot, which is also x1 dot, and this is given by this part of the equation just now we've seen. Okay, and since u is linear in control, we can formulate the u directly from the balances, the heat balance. Okay, so u is given in this form. Okay, let's say this is the x1, and these are all the dimensionless variables. It depends on the parameters, the variable x2, x1, and so on. These are the other parameters within the system, and it's dimensionless, so it has other parameters like heat transfer coefficient and all that within its thing. Okay, we have no detail. Yeah, you can go back to your chemical engineering books and see the formulation what the beta phi means. But it's dimensional just to make it easy. Okay, this is typical example. Not you don't have to strictly follow it, but this is good enough to explain the method. So once we get u, and we know that the GMC formulation is given by this y dot equals to k1 x set point minus x1, okay, which is the y equals to s1 plus k2 to integrate the x1 set point minus x1t. So we got this, and we got the y dot given here down. Okay, sorry, and we go down, then we will be able to solve the GMC method. Okay, not detail here, but you can go to and see that we can solve, get the k1, k2, and put it in, and we can solve for the u in that case. I'm not able to go back because it's lose the thing, but you go back and see what happened. Okay, that we start off to that point just now, but you can try yourself and see what the GMC for CSTR and for other equation as well. CSTR is just an example, but it can be used for any other system that you want, process computer system, whether it be linear or non-linear system. Okay, if you have one, see the second option that we like to control x2 now. x2 represents the concentration, mass, from the concentration from the mass balance just now, CSTR. So that means the if you talk about x2, then the y is the x2. Is the output that you want to measure, the output that you want to control. So the y will become the x2 that you're looking for. Okay, and if you put the GMC formulation for this one, then we can have to do this, y equals to x2 dot. Okay, and we get the right hand side of the equation. But from the equation that we've seen just now, the heat mass balance and its mass balance, the u does not come out. The manipulated variable, whatever it is, and CSTR normally is the cooling water, or for endothermic is the steam injection to the jacket. It does not come out for this balance. So what does it mean? It's not only talking about whether linear or not, it doesn't even come out, doesn't exist. So there's no U that we can formulate to implement it using the GMC method in this case. Okay, so if the U does not appear, that means the GMC cannot be applied in this case to control the X2 for this case. Okay, the GMC can be used to control the X1, but it cannot be used to control the X2 because there's no direct explicit formulation between the output and the U, or y output differentiate output y dot, which is equals to X2 dot. There's no relationship at all, so we cannot get the U, and so we cannot use the controller to control the X2. So we can only control X1, and hopefully by controlling X1, the X2 will follow through. Not exactly, but it should follow through what we require. But if we have both, then we need to have multi-variable control. But if you have one, then if we can control one, then the other should follow closely to it. In most cases, okay, not every time. Most cases. So this is a multi-variable control system. You can decide one of them, and the others you inference that it should follow the set point. But if you have two different set point, then we may have to think about using other methods. If we want two variables to control at one time, X1 and X2. Okay, but in this time system, it's only able to control the X1 because the formulation for GMC only is able to be fulfilled by the X1 dot X1, not dot X2 dot. And the other thing is also GMC can be used with state and parameter estimator, because at the end of the day, we need to be able to measure the output. Okay, the output of the process is needed. For GMC, you need the output y. Say y equals x1 dot. It's very important for us to be able to measure that, because we need the error, the actual measurement, set point minus the actual measurements. We're not able to measure, we're not able to implement also the GMC. So in most cases, we should be able to measure, but in cases where we are not able to measure, we may have to do state and parameter estimation methods. You may have studied before, okay, using GMC, so using Kalman filters and other observers, we can implement that into the GMC if we have the estimation of that variable. So similarly, state and parameter estimation is applied to estimate the unknown or uncertain parameters as well as the unmeasurable state. So if we have any of the states unmeasurable, we can use this state parameter estimation. Sometimes measured, but some parameters inside it are not measurable, so we can also use state parameter estimation. Okay, sometimes temperature we can measure, but the heat released inside the exothermic equation, and so we are not able to measure. So we may have to use state and parameter estimator. Some coefficients that is needed, we may not be able to measure, so we have to use parameter estimator. We can use some values which is not accurate. Again, depends highly on this method we mentioned just now. It depends highly on the accuracy of the model. So if the model is not accurate because some parameters are not accurate, not well known, then the whole thing also break down. So we have to implement the GMC with known parameters and known state variables, which can be measured. That's fine. It cannot be measured. It has to be estimated well, so that again it goes into the GMC. So we have the process output goes to GMC, but some state or parameter that we need to estimate, we estimate it and put it back into the GMC to come up with the input with the U, the mental variable into the process. And then only we'll get a reliable U that we can use it to implement our GMC method, because we have a reliable process estimation. The parameters are reliable, so the GMC should come out as also a reliable GMC. Again, because GMC depends on that formulation, okay, the model, and also the measuring the models and the parameters. Of course, you also need the tuning. A1 can tune is okay. That part we can use the method that we said just now to get the tuning, but the model has to be also good. Just having a tuning for non-certain model is no point. right? Okay. So see, in summary, JMC is a simple nonlinear control strategy. Okay, it's not only non-linear, it's also can be used for linear, but again, as I said, linear, normally we can use other methods. PID, PI, conventional, good enough for linear most of the time, but it's more for non-linear. So it's simple non-linear control strategy. Okay, or also again, simple control strategy that is much easier to understand and implement than other control techniques. You can see it's quite easy to understand. Direct formulation, K1, K2 integrate and plus the Y dot, Y differentiate. So it's a very simple understanding, very simple formulation. It's not complex at all. If the model is complex, then the formulation is slightly complex, but model is okay, it's typical, and we can easily use that formulation. This MC can apply to control success in a real nonlinear process as long as process models are available. That's again the issue. Process models in plant, real plant, it has been done, as I said, can be done as long as we have some process model reliable and we are able to measure them, parameters, and so on. But whatever it is, with state and parameter estimator can handle this plant model mismatch of a certain. So we have unknown, as I said just now, state or parameter. We can use the state parameter estimator like a Kalman filter normally to be able to handle this model mismatch and take care of the uncertain parameters. Some are more certain, some are uncertain, and so on, or unmeasured parameters, unmeasured variables can be handled using this estimator. To that we can implement the GMC directly. The formulation can be implemented directly. And again, as we mentioned just now, it's limited to those systems which are linear in control. Okay, where your U can be formulated in terms of the other variables. So that's linear in control. Okay, or you have what you call the function when you differentiate y, the U should come out directly as a straightforward linear in control. Linear, it should be a linear part of the U, so that before we can properly implement the GMC method. So this is one of the biggest what do you call disadvantage basically, yeah, but also an advantage in certain ways because the U is directly linear, we can easily implement the U, but also in that many cases as we've seen just now, for x1 we can formulate it because the U comes out, we can get it in terms of linear, U linear, but when you use the output as x2, it's not the same. It's not there. It doesn't exist, or sometimes it exists, but as I said, it is not linear. So we also cannot use it. Say u square root u equals to something. That's something that we cannot use because if we want to get u, we have to square the other side. Or u squared equals to something, we want to get u, we have to square root the u. So we lose the accuracy. Okay, square root not so bad. The other side, where u squared, u cubed. To get u, you have to cube the right side or square the right side. Then you lose the whole accuracy of the u formulation and so on. As you know, when we square it, or we take the cube root and so on. Okay, so the accuracy is lost, the simplicity is lost, the direct formulation lost, the linear in control lost. So many issues come out when the U is not linear in control. Okay. Some application, you can see so many applications, especially simulation. There's lots of application. They're using the GMC method, but some of the typical ones that have been done in the pilot plant, and some industries have used it before, especially the traditional industries, the pulp and paper, and so on. When it was developed in Australia, they had used it in their industries in Australia, especially. It's being used in other places as well, but in simulation, of course, a lot. Okay, issue again because why is not? It's very easy, simple method. It's good method. Again, because of the model formulation, that we cannot get linear control, or the model is complex. That it's not easy for us to get the model good enough. Right? If it's complex, then you can imagine many variables are not, many parameters are not uncertain, and so on. It becomes difficult to keep on estimating and to keep on getting linear in control and so on for some very, very complex system. Okay, so what were the applications for? If you look at the common one, the most popular one, again, a vector system. Seen just now, so a vector in which one or more exothermic chemical reactions are occurring involves high nonlinearity and potentially unstable operating points. Therefore, the control vector demands practical and robust control. Robust can be used for uncertain parameters, for nonlinear systems, a wide range of operating is robust, and that needs a practical one, and that cannot be handled by the conventional linear methods like PI, PID. So we need to go into advanced control, and one of them that is clear and straightforward is this GMC control method. And we have a system with two parallel exothermic reaction and a batch reactor, especially. Okay, again, for batch reactor system is highly nonlinear, difficult to control, got a profile, and this is where GMC comes in. And in this case, the control aim is to heat the reactor contents quickly, okay, from an initial temperature to a desired final temperature, and control it at that temperature using GMC technique. Okay, so basically we want to control it at a certain profile. Heat vector and reach a certain profile, and that's not easy to be achieved using the normal conventional method. It's not just one set point, but a profile of the set point. And this always happens for batch system. Normally, they also have some control in the system, but batch system we need normally a profile of the set point and temperature set point. So from an initial to desired and control it at that temperature using GMC. Then GMC is reliable technique when you need this, and when you have a good control. Just you could got a good model for some batch system. We may have a good model, and we can use it easily for that sort of thing. Again, we need to see where, okay, in this case, this batch where we are having batch reactor. So we are this is exothermic, so we're cooling down the jacket, but the cooling is done outside. If take out the water, the cooling part, jacket part, we cool it here. Okay, I want to heat it or cool it, depends whatever, whether it's exothermic or whether it's endothermic, will depend whether you need the cooling or you need the heating. Whatever it is done outside, external, then send back to the jacket. This is one way of operating batch reactor. We can have the jacket itself as the cooling, that we've seen many cases, but sometimes people prefer to have this for batch, and also maybe continuous system sometimes, to take it out, cool it, and send it back to the jacket where it will do. So the control will be inside here. The heat exchanger will be controlling the temperature of the jacket by whatever temperature of this output stream will go to the jacket, and that is the temperature that you're controlling it to. Manipulated variable to get the profile of temperature inside the batch reactor. Okay, inside this batch reactor, and this is quite, and you can say, quite challenging, quite difficult in some ways. It has to be done very accurately. So GMC can be used. Once you get this, what you have to do, get the model, the system. This is quite standard batch reactor, so you can have a standard model for the subsystem. Put it into the model system, the ODEs, okay, for mass balance or heat balance, whatever. But then we have to see whether if there's a U is linear in control, which equation we can use. Some equations don't have U linear, some have U linear in control, and so that equation can be used just like just now. X1 we can use, X2 we cannot use. So we decide on that to decide what is our Y1 and what is our Y, what is our manipulated variable. And this has been implemented in the pilot plant. So for this GMC control diagram, this is the equation. Again, the Y dot equals to K1 error, K2 integral of the error, and we're using an energy balance around the vector contents. Okay, so this is the temperature of the vector, and this is the other parts. Okay, the Q, U, and A. Okay, then typical reactor, heat release and the heat transfer coefficient, the area, the flow, the heat coefficient, and the Tj minus Ti. This is going to be the Tj is basically the heat of the temperature of the jacket, manipulated variable, and the temperature of the vector. And replacing TRM for Y, this is what we are going to. Y is the actual temperature of the batch. That's Y, right? And TRS set point is the Y set point. So we get this, and we will get the control input. Okay, control input U, which is the TJM. Okay, the TJM, the temperature of the jacket, right? And given this is the other side, so you can get U here, direct here. So this is linear control. The U is TJM. You can formulate U in terms of the other variables, which is equals to this part, the right hand side, and you have the K1 tuning, K2 you have to tune, set point we know what is the set point, whether it be profile or one direct number, doesn't matter, and minus this value. So all these values depends on the parameters of the models. So we have them, we can use it. We do not have to estimate. The one that most probably for us more difficult to get is the QR, because this is the heat release. It is something they're not able to measure. Normally we don't, it's not simple to measure the heat release. Yeah, so we may have to estimate it, as I said just now. The estimate is important. Okay, the U, A, and all that, we can somehow get it. Again, if they are not able, we can somehow estimate it. It's not as critical as the Q, which is not able, because we are not, there's no measurement for QR, and that's a very important part of the whole equation here. It's quite big term, and if QR is not accurate, the whole thing becomes inaccurate. Not only the model, but the parameters has also to be accurate, and significant parameters like QR is important. The area maybe not so difficult to get, the flow and the CP, something quite standard for the certain fluids. Area and the heat transfer coefficient not too far off. Again, not accurate, we cannot get accurately, but some maybe not too far off. So the QR is something that is dynamic. It's also changing very rapidly with the time, because the whole system is a CSTR, and the CSTR depends on how much heat release that will make it able to be controlled easily or not. So once you get that, so we have to estimate. We have the estimator, we implement it. We have to measure some and measure the temperature. We can measure, and the QR has to be estimated. Normally, as I said before, we can estimate it using the common Kalman filter methods. Right. And we transfer it in discrete form, because in the real computer implementation is to be discretized, so just the discrete time in terms of k at what sampling time k. Okay, and the integration is given of summation. Tuning we get from the graph just now, as I told you, and just implement it in discrete form, because it's going to be normally the discrete implemented in the computer, which automatically is in discrete form anyway. But here we can see much clearer the discrete form implementation for this sort of advanced control method. And as I said, implementation requires the knowledge of the system parameters WCU, the measurements of TR and the TJM, the Ys and the U, and the U is also measured, because actually the set point is not the U itself. The set point is the TJ set point. We fix what is your TJ set point, then we try to make the TJ follow that. So TJ we can still measure, but the actual manipulator is the set point of that we want to get for the TJ from the heat exchanger itself. Heat exchanger set point is basically the TJ set point that is being used, and to measure TJTR, and also we have to get estimate of QR. So I said the QR is something that is not normally possible to be measured, so we need to have an estimation to implement this whole system. Once we have that, then we can implement this. Of course, K1 and K2, again, that tuning depends on the graph I showed you just now. Whatever zeta we want, whatever time, how much time response we want, we can roughly get the K1 to as initial estimate, and then later we can keep on fine-tuning it to the profile that we want for our methodology. So basically, for estimating the Q, we can use the finite difference approximation, but there's quite a lot of errors involved for that. Or we can use, as I said just now, the Kalman filter on the simplified process model. Again, a more simplified process model, just to get the estimation of just the Q can be used, or we can use on the rigorous process model, but there's too many unknown, but it's not so necessary. As long as we get a very simplified process model, we can estimate the current filter through the computer, the Q head release, which is good enough in many cases. But if you want it to be more accurate, you can use the rigorous model, but then there's so many unknown parameters that makes it more difficult to implement online, especially, and we lose the purpose. We don't mind having rigorous process model for the GMC implementation, but to have it also for estimating the the model parameters, then it becomes too heavy burden. It becomes maybe slow, late, and it defeats the purpose of using the simple methods like GMC for that sort of case. Okay, so but anyway, we can have the choice to the parameters for QR or for other parameters in other situations. We can use all the different methods. And there's one way where you can use the heat release model and estimate the Q by this sort of method. Okay, the simple, not so difficult, not so simple, but good enough to be used to estimate the Q release and implement it back into the GMC formulation to get the U output variable output. Okay, we can go to this later detail, you can see, but roughly this is one of the methods other than the Kalman filter methods and so on. And state equation. So if you use Kalman filter, then this is the sort of method that you will use. You need two measurements and can be used to obtain the estimates of the states. Okay, this is again using the model of the equation and using the heat release sort of model to get the QR. Okay, and two measurements are able and are used to obtain the estimate of the entire state. So mainly this in case we are estimating the QR to implement into the GMC. Okay, because the main purpose is to get the manipulated variable U, which we mentioned just as TJM, but in the real world is the TJ set point that is being used to get the TJM to follow that TJ set point for this sort of cases. And again, information flowchart, we have the TJ, TLM measured, we have the Kalman filter to measure the heat release Q, put into GMC, and then get the TJ set point, okay, which I said is the actual manipulated variable. Then the TJ, by controlling the TJ, we can get it follow the TJ set point. Here we can use the for the heat exchanger, which is the cooling part or the heating part, we can use the PID to get the TJ to follow the TJ set. Once you get the TJ right, then it can be used to with the Kalman filter to be implemented in GMC. The TJ follow the TJ set point means it's following the profile the GMC has come up with. Okay, profile given by GMC. So that's an experimental result. You can see it clearly, but basically initially estimates are not good, so it runs away, oscillates, but slowly it follows the profile. This is a set point, and this is the actual one slowly following. This is a batch system, not easy profile, but slowly it's picking up. This is the estimation for the Q estimation and for the jacket TJ. Okay, the Q also some oscillation, but slowly it tries to follow the heat release accordingly to what the model is, and slowly the profile of TJ going to what it's supposed to go, and then to get the TR to follow this profile. Okay, using GMC is not easy. I think you can see it's quite difficult system. PID may not be able to get this profile nicely. This is real world, not simulation. Experimental result, a lot of noise, but it's able to still handle it within the constraint, close to what we want. Another result also not so good this time, but still just to show that you have initial estimate, it runs, but slowly it picks up, tries to follow the profile. It's like offset, but still the profile is there, still following the profile up and down, maybe with some offsets, but it's not totally run out of control. Again here the TJM following closely, but here the problem here is because of this heat release. Okay, it's quite oscillatory and quite off, and then slowly starts to come, trying to pick up slowly. So it takes some time. So we follow it at the end for some time, we go slowly. And this one, because this one slowly following what it's supposed to be, and this one also going to what it's supposed to be. If they are what they're supposed to be, then it also should be what it's supposed to be for the TR, the control output Y. Okay, but just to show that this difficult system is not easy, especially online, unknown parameters, unknown QR, unknown, many unknowns, a non-linear complex system-based system. So it can somehow work quite stable, the GMC. So it shows how easy to implement, how good to implement for non-linear system, how useful for advanced control system, how much GMC has got can stabilize the system. At least it's still stable. It's not way out of stability. Initially, yes, it's unstable because unknown, a lot of unknown measurements slowly, but once this one gets to pick up to the actual profile, and this one also slowly pick up to the profile that we would like to have. Okay, so this is the MC method. It's nothing to do with the PID, PI, except just some tuning, and so it's the modern methods. It's not the classical method, which is quite closely related to PI, PID, or have the same motion. This is totally different. So on feedback structure is different, and way of implementation is different. The formulation is different, and also this can be the modern methods also, because it's using computer based. You need to computer to compute that. You can't do by hand, cannot do on paper. You need to computer to compute. Of course, you have to connect it to the DDC, directly to the computer. Once the measurement ends come in, it measures, calculates, then it comes up with a manipulated variable. And that's no typical modern methods of advanced control, which needs computer based. We will see later other advanced control methods, MPC more computer based, typically more comprehensive, which we just mentioned to you in the first class. I don't will teach you, but also the AI methods, fuzzy neural and so on, they are dependent on computer. So these are under the modern based methods and so on. Okay, so thank you very much. I think all we have. So if anything, we'll discuss in the last class, or anything, any questions, anything we can discuss in our last lecture on the GMC method. Okay. Okay. Thank you very much for your time, and hopefully you'll go back and go into some of the details you have not gone to. You can look into it in the formulation of GMC, the modeling, how to get the model, and also the tuning part, and also the estimation part. And have a look at it more detail. Thank you very much, and okay, stay safe all. Bye.